Data is the new gold. It is estimated that 90% of the world's data was generated in last 2 years alone. By 2025, more than 150 zettabytes of big data will be used for analytics. And when it comes to data analytics, we need to manage batch data, real-time stream data, or even near real-time stream data. That means we need to collect, process, and transfer data to data lake or data warehouse. We have many tools available in the market, some open source, some proprietary. But Apache Kafka wins this space and race. More than 80% of Fortune 100 companies trust and use Kafka. It's needless to say why you should learn Kafka. Hello fellow tech enthusiasts, friends and families. Welcome to our new video. Today we will explore Apache Kafka. If you are looking for a course to learn Apache Kafka fundamentals or want to brush up your concepts, then you are at the right place. If you watch this video without skipping any content, you will have a solid understanding in Apache Kafka. Let's start today's video with the course outline. We'll start with what is Apache Kafka. We'll use a real-life use case to understand the concept. Followed by, we'll understand why we need Kafka and what problem does it solve. We'll browse different Kafka use cases and industry trends. Next, we'll review Apache Kafka Enterprise Architecture. Following that, we will review Apache Kafka Topic, Partitions, and Segment. Subsequently, we'll review Kafka Broker and how data replication works at a Kafka cluster. Afterwards, we'll discuss Kafka Producers and different producers aspects. Then Kafka Consumer. Thereafter, Kafka Consumer Group. And at the end, we'll review Kafka Consumer Offset. Throughout the course, we have used real-life examples, animations, and illustrations to make the video interactive, effective, and easy to understand. If you encounter any challenge understanding a concept, please leave your queries at comment to this video. We provide prompt reply to any comments. We have a lot to cover. Let's jump right into today's topic. If we look back 10 years, we had monolithic applications or 3-tier architectures. However, with the advent of microservices, the monolith code base started breaking into small independent services called microservices. In one end of the spectrum, we have the producers producing the data and consumers on the other hand. In today's world, we are dealing with diverse producers and consumers with heterogeneous schemas, interfaces, tech stacks, and they all are interconnected in a tightly coupled way. If we want to add couple more consumers or producers in conventional approach, we need some tweaking in the existing systems. As the data source is growing exponentially, collecting data or integrating these systems turning more difficult day by day. And in place, we all want loosely coupled producers and consumer. That means we should have the capability to add unbounded number of producers and consumers into our application. Exponential increase in concurrent producers and consumers will neither slow down the system's performance nor hamper its throughput. We need super fast processing, and throughput will not depend on the number of sources or sink. Data is coming chaotically from different systems. But while processing, I should process the data in the order of generation. And last but not least, the end outcome or inference the system will generate should be highly accurate. Uber is one such application that meets all of my desires. Let's examine Uber's use case and explore why conventional architecture or processing method may not be sufficient, and why we need a solution like Apache Kafka. When I book an Uber or request for a ride share, the Uber application started providing me estimated time for the driver to arrive and the pickup ETA, an estimated fare for my trip, the car's real-time location and tracking, estimated time to drop off, and the ETA updates in real time based on the traffic condition. Also, the driver's population in my current location along with different vehicle size like Uber XL, Comfort or Share. As soon as I start my ride, I'll start getting route information along with the estimated time and distance to destination. Also, the vehicle's location with live traffic condition. Let's assume I am at point A and I want to go to point B. To provide all the details and statistics to me, Uber maintains some backend systems like geolocation, map API to interact and visualize real-time location in a map interface, ride analysis, ride history, and real-time feed like the Uber has arrived or the driver is appearing to a location or you are using a payment card for this trip and you don't need to pay driver for cash, something like that. If you are familiar with Uber or the rideshare, you must be getting all those messages in your trip. Now, if you want to implement this solution using conventional approach, we need a server and a database. And this server will retrieve the current location of the vehicle and then store the data inside a database. Now let's assume this server is getting the location or the get location and then it is pushing the data into the database. Then the data will be fueled for all other modules like get location, map API, ride analysis, ride history, and real-time feed. For a real-time tracking, I have to collect this data every now and then, maybe every second. Again, the same process in the next point after a second, maybe I am at point C. Again, the service will collect my location and it will push the data into a database, then parses the data. After that, it will flow that data or information into other applications. Now let's review some trip statistics from Uber. In the year 2022, Uber completed 7.7 billion trips. During 2023, the number jumps to 9.6 billion trips. This shows the volume growth and the robustness of Uber application. If we consider 1000 users per minute for our example, which is very low, consider Uber's global reach. But then also, can a conventional database deliver that throughput? The answer is no. Considering that high throughput volume, the application will crash. No way our database will be able to support that user's growth. The single sentence answer to any conventional, rather legacy data collection and data processing system is they won't be able to handle that type of interactions. Now we have multiple application use cases and consider any social media websites or maybe manufacturing industries. We need a distributed system with massively high throughput and Apache Kafka is one of the service having this capability. Let's review how Apache Kafka can help us. If you are new to our channel or haven't subscribed yet, please subscribe to our channel and please click on the bell icon to get notification for any new topics. It may take less than 30 seconds from your valuable time, but it will greatly motivate us to create future content like this. Let's continue with the topic. Before we explain how Kafka has resolved Uber's business challenge and how Kafka has been used to run Uber, let's review what is Kafka. Kafka is a distributed event source and stream processing platform It's an open source system developed by Apache Software Foundation and it's written in Java and Scala. Kafka aims to provide a unified, high throughput, low latency platform for handling real-time data. Kafka can collect data from distributed and diverse systems, process the data, and store and integrate data at scale. In terms of systems integration, here are some category of applications you can integrate with Kafka to send data to a Kafka cluster. To start with, IoT, web or mobile applications, you can have custom applications, microservice, or you name anything, or even social media applications, or maybe monitoring applications from different manufacturing industries, or even a data source which can emit events. At the south side of the diagram, to represent the applications which can consume data from Kafka, we have web application, we have SQL databases, we have NoSQL databases, we can have data lake or even data warehouse like Hadoop or other open source data warehouse or cloud data warehouses, or we can have monitoring application, real-time monitoring applications, or even we can fuel a machine learning application which can consume data from Kafka. The top layer which push data to Kafka cluster is called producers, and the bottom layer which processes the data from Kafka cluster is called consumer. Kafka has the capability to collect, process, store and integrate data at scale. But if you are thinking, will Kafka replace database for my application architecture? Or is Kafka a replacement for conventional databases? Then answer is no. Kafka is not a database replacement. Are you confused? Let's find the answer and let's review how Kafka differs from databases. We discussed that Kafka has a very high throughput. It can be scaled massively and throughput does not depend on number of connected producers and consumers. If you are not familiar with throughput, then it's the unit of data or messages a system can process at a given time, maybe by minutes or maybe by seconds. We also know that databases has lower throughput and directly proportional with the number of connected clients. However, database can persist data into any database for a real long time, maybe for 5 years, 10 years, and even more than that if we need to. On the other hand, Kafka is like a pipeline of data. Kafka is not meant to persist data for a longer duration. By default, Kafka cluster holds data for 168 hours or 7 days. However, this is not a hard limit and the retention period can be adjusted according to the needs of your application. Once you write data into a Kafka topic, it's become immutable and you cannot modify that data. You can update the data and resend again to Kafka cluster, but that will be treated as a new data. In a database, you can create index to speed up your query performance, like you can create dense index, sparse indexed, or maybe a secondary indexed. But as of today, it's not possible in a Kafka topic or in a Kafka cluster. Database supports complex queries with subqueries, joins, different type of joins. On the other hand, Kafka supports KSQL DB, but not meant for complex queries or queries with joins. Please drop your comment if you are still not clear in what use case you should use database and where should you use Apache Kafka. But in a single sentence, Kafka and database are not alternative to each other. They manage different segments of data analytics architecture. Now let's review Uber use case using Apache Kafka. In terms of producers for the architecture, we have rider app, driver app, which are constantly sending stream data into my Kafka cluster. Now there are APIs or services to connect and host external services like Map API, payment services, or integration with local law enforcement agencies, and etc. etc. Now, Uber expanded into multiple segments like food delivery, package delivery, and all. And we may have some services for dispatch or even for logistics. These are just some examples, not the entire list. They are creating data and pushing the data constantly into a Kafka cluster. Now, in terms of consumers on the right hand side of my diagram, we have mobile applications. It could be rider app, it could be driver app. They are also the consumers of the platform. Then there are real-time alerts. We also need to collect the geolocations or publish into geolocations or map APIs. Kafka supports PubSub messaging or publisher subscriber messaging protocol to integrate these use cases. Then real-time analytics. We can integrate with Apache Flink because we need stream processing and batch processing framework. Then debugging to trace, audit any issue, maybe bugs or system problems. We need the log data and we can use ELK or Elastic, Logstash and Kibana's tech stack to integrate. Additionally, we need to store these data into Uber's internal database for future processings. Now, on top of that, Uber performs multiple data analytics work like AI ML to detect any anomalies or detect fraudulent writes or detect fraud transactions. Then they also perform some ad hoc explorations of their data and also the reporting for their business purposes and also different type of reportings, recommendations for customers. All these are data analytics use case, and for that we need a data warehouse where Uber is using Hadoop. Now they integrate Hadoop and they are getting the data from Kafka cluster. Now in my entire architecture diagram, if I break that section into two parts, the north part or the topmost part where we have the real-time pipeline or real-time data processing, and the bottom part is for batch pipeline where we are processing the data in a batch. And we can see that Kafka supports both those use cases for real-time pipelines and for batch pipelines. Now let's review Kafka use cases. To start with, we have messaging system. Kafka offers better throughput, built-in partitioning, replication, and fault tolerance. We'll explore all these concepts, what is partitioning, what is replication in our future slides. And this will make Kafka a good replacement for traditional message brokers like RabbitMQ or any other message brokers. We can use Kafka and we can create a real-time user activity tracking application for our websites. We can use Kafka for metrics aggregation, and we can aggregate statistics from distributed applications and produces centralized operational dashboards or metrics. Then we can use Kafka for log aggregation, and we can use as a replacement for conventional log aggregation solutions. We can collect logs from distributed applications and publish the log into a centralized log processing area. Next, we can use Kafka for stream processing. If you have a streaming data source, it could be a real-time streaming or near real-time streaming. You can use Kafka to collect data from these data sources and push the data to a centralized location like a data lake. We can also use Kafka to perform ETL process on the data. To explain the concept, let's refer the medallion architecture where we have bronze tier for the raw data, the silver tier for the filter and clean data, and then the gold tier for the curated data. And we can perform any machine learning or AI ML process on top of the gold tier or the curated data. We'll explain the Kafka topics in a future slide, but let's review how we can implement the bronze, silver, and gold tier using Kafka architecture or using Kafka topics. For that, we have to create different Kafka topics. Let's say here is my producer, which is producing the data, and I can use a Kafka topic where I can push all my raw data. So this is your raw data. And producer is pushing the data into my raw data topic. Now I can add ETL process to filter and clean that raw data. Once the data is filtered and clean, I can use another one Kafka topic where I can push the data. So this is a second Kafka topic where I can add the clean data. And my ETL will do the cleaning process. And you can see here, I can directly integrate a ETL job or ETL process with my Kafka cluster, and I can maintain different topics, one for raw data, one for clean data. Similarly, I can create another one Kafka topic to host the curated data, and from there I can run my machine learning application. But as a best practice, since Kafka is not meant for data persistence, normally we should store the curated data into a data warehouse or to a storage where we can persist the data for a really long time. However, the raw data and processing the raw data to create the filter on the clean data, we can directly perform inside a Kafka cluster. That is how Kafka can help you for end-to-end streaming processing or the streaming data use cases. We can also use Apache Kafka to decouple system dependencies, and we can implement event-driven or event sourcing pattern to loosely couple my producers and consumers of the applications. We can also use real-time analytics. I can process and analyze data as soon as it arrives. Then also I can use for any data integration use cases. If you have thousands of microservices in your environment, you can integrate diversified systems into your Kafka cluster. Now let's review some Kafka users or some big organizations who are using Kafka. And this is not the entire list, this is just a subset starting from LinkedIn. And for this LinkedIn use case, Kafka was initially created. Then Netflix, Airbnb, Yahoo, New Relic, Walmart, Uber, Spotify, these are just few names. The next diagram, this diagram hope it will give you a clear picture that how Kafka is used and trusted by multiple organizations. These statistics is directly from kafka.apache.org website, and they are claiming 10 out of 10 manufacturing industries, 7 out of 10 banks, 10 out of 10 insurance industries, and 8 out of 10 telecom industries are using Kafka. I believe now you get a feeling that why you should learn Apache Kafka. Now coming to the emerging trends to use Kafka as a service, organizations they are using Kafka in cloud, and this approach allows business to leverage the capabilities of Kafka without the need to manage any underlying infrastructure. Nowadays AWS is also coming with managed Apache Kafka cluster on top of their conventional services like Kinesis and all, which are also a streaming platform. But again, Kafka is more widely used than all other cloud native services. Now let's review Apache Kafka architecture. The heart of this architecture, we have the Apache Kafka cluster, where we have one or multiple Kafka brokers. The good number to start with should be 3 brokers, and we'll see why we need at least 3 brokers. But a big Kafka cluster can have hundreds of Kafka brokers. On the left hand side, we have the producers who are producing data or pushing the data to this cluster. And to connect producers with the Kafka cluster, we have Producer API. On the right hand side of the diagram, we have all those consumers who are consuming data from these Kafka clusters, and to connect them, we have consumer APIs. Then again on the left hand side, I can import data as an event stream from different cloud services, databases or other systems. And to import data as an event stream, I have Kafka Connect. And if I'm talking about the producers, then the API would be Kafka Connect Producer API. Similarly, on the consumer side, I can export data as an event stream, and I can use cloud services, different databases or other systems. And to integrate, I am going to use Kafka Connect Consumer API. The API is called Kafka Connect. From consumer side, it is consumer API. In producer side, it is producer API. Then there is a third component where I can perform the compute, or it is the compute layer of my cluster, where I can create, process and query event stream data. I can also create temporary tables here. And for that, we have Kafka Stream APIs. For producer, that means to create and produce, we have Kafka Stream Producer API. And from the consumer side, we have Kafka Stream Consumer APIs. Now to summarize, at the middle of the Kafka architecture, we have Kafka cluster, which consists of one or multiple brokers. In the left hand side, we have Kafka producers who are producing data to Kafka. And in the right hand side or on the other side of Kafka cluster, we have consumers who are consuming data from Kafka cluster. And we have different type of APIs, producer APIs for producer to directly connect. Then Kafka Connect Producer API to import data as a stream event. And then for compute layer, we have Kafka Stream Producers or Kafka Stream API. Similarly, the same API will be replaced with consumers when it comes to consumer. Throughout this course, we talk about Kafka topic multiple times. Let's review what is Kafka topic. Kafka topic is a stream of related messages. It's somehow similar to your WhatsApp group. In your WhatsApp, you may have different groups, maybe one group for your office, one group for your sports, one group for your kids pickup, or maybe one group for your kids school. And all different groups you are talking about the relevant subjects. Like the same concept is applied to Kafka topics, where the related messages are grouped into streams. It's like a table in database, but without any constraints. One point to remember, by default, Kafka stores data for 7 days, and that is not for long-term persistence. Now, every topic that will be identified by a name and data must be created in a topic. When you are trying to create a data, you have to mention what topic you are going to write. You simply cannot connect to a Kafka cluster and push the data. We have a Kafka cluster, and then in the left hand side we have different producers, and right hand side we have different consumers. I am sorry for this typo. This will be consumers. Now we have multiple topics, and producers are producing data to a particular topic, and consumers are consuming the data from that topic. You must be thinking, do I have to maintain one producer per topic? The answer is no. You can have end-to-end relationship between producers and the topic. That means you can put data into multiple topics from one producer, or you can use only one topic to collect data from multiple producers. You can create unlimited number of topics, and topics are split into partitions. Now let's understand the concept using a diagram. Let's say I have my Kafka cluster, and there I have 3 topics. Now these topics are further distributed into small partitions. If you are familiar with databases where you are maintaining certs, or maybe if you are familiar with the DynamoDB table where we have multiple partitions, the same concept applied here. One topic is distributed or divided into multiple partitions. Now one partition can be further divided into multiple segments, and this is just like rolling log files. Inside one partition you can have multiple log files or multiple data stores where you are storing the messages. At the top level you have topic. Then topics, one topic can be divided into multiple partitions, and then one partition can be divided into multiple segments. Now let's understand Kafka topic in a greater depth. We already saw topics split into partitions. When you are sending message inside a partition all those messages will be ordered. And messages are ordered using an incremental ID which called offset. Let's understand that concept. Let's say we have a partition 0. When we'll first push one message, it will create 0, then 1, 2, 3. Like that way, it is going to create incremental number, and this incremental number is called offset. What will be used to read and track the partition when the consumer is reading the data? We can have multiple partitions, and inside each and every partitions will have separate offsets. This is all together, it's a Kafka topic. So one Kafka topic can be broken into multiple partitions. Producers are producing message into these topics. Now, producers send the message into a topic, and Kafka distributes the messages randomly into partitions. Message ordering is only guaranteed within a partition. Let's say within this partition you have this 0, 1, 2, all those offset values, and that offset is only applicable for partition 0 only. Maybe one message offset 6 in partition 0, that message if you want to push for the second time, and if Kafka decides to deliver that message into partition 1, it may not have the same offset. It can have a different offset based on the available incremental ID to that partition. Offset is only specific for a partition. From producer point of view, producer writes the data into a topic, and Kafka randomly assigns the data into any partitions that Kafka balances the load or Kafka wants. Data inside a partition or topic is immutable. The moment you will write the data inside a partitions, you won't be able to change the data. If you want to change any data or any attribute or update the message, you can update the message and send another one message to Kafka. Now Kafka might put that into the same partition, or it might put into a different partition, but the message will be treated as a new message. Kafka never revisits an offset within a partition. So let's say I have the data persistency limit, or the default data persistence value is 7 days. So after 7 days, all my 0, 1, 2, 3, 4, 5, these offsets will be wiped out from the Kafka. Now if I am sending new message to this Kafka, and if that message will land into this partition, it is going to create a new offset value. It is not going to reuse these previous offset values where the message is already expired. That is why one offset, if it's already used by partition, it will never be revisited by Kafka. Let's review Kafka Broker. A Kafka cluster can have one or multiple broker nodes. 3 is a good number to start with, but some large Kafka clusters can have hundreds of Kafka brokers. We saw that one Kafka topic is broken into different partitions. Kafka topics are distributed across the broker. Let's assume that we have 3 topics starting with the green, blue, and the orange. And we can see that Kafka topic 1 that is distributed across the 3 broker nodes, whereas the topic 2 or the blue topic that is distributed between broker 2 and broker 3, and the orange topic is distributed to broker 1 and broker 2. Kafka topic will be spread out. Not every broker will have every topic's partition. You can see broker 1, it does not have a topic 2 partition, and broker 3 does not have a topic 3 partition in my case. You must be asking that then how I am going to read and write data to this Kafka cluster. From writing or reading point of view, once you will connect to any one of the broker, you will have access to the entire Kafka cluster. So while pushing the data, you connect to the Kafka cluster, you connect with one broker, and then you mention the topic name using this syntax when you are trying to push the data, and Kafka will automatically distribute that message into different partitions that is available within the broker nodes. Similarly, when you are trying to read the message from the Kafka, you are going to connect with any one broker node, and Kafka is intelligent enough to find out where that message is or where that partition is. Maybe you want to read from topic 2 and the topic 2 is not available in broker 1. Then also if you connect to broker 1 and trying to push the message for topic 2 or try to read message for topic 2, you do not have to go to the broker 2 or 3 node. Even if you connect it to broker 1 node, Kafka will be internally route those messages for you, and it will help you to push those messages into proper topics or proper partitions and read the messages from the proper topics or proper partitions. Now you must be asking, if a broker node die, will I lose my data? The answer is no. And we can achieve the same thing using replication factor. Normally, your topic replication factor should be greater than 1. Let's say you have replication factor as 2. That means your partitions will be replicated into more than 1 nodes or 2 broker nodes. In my example, I have used replication factor as 2. That is why all my partitions has one more replica into other broker node. To start with, partition 0, it has a replica to broker node 2, and partition 1 has a replica in node 3. Similarly, all other partitions is replicated into any other broker node. Now let's see that if any one of the broker node dies, for our example, let's say broker 3 dies. Now my Kafka cluster will be able to serve the data from rest of the brokers. And I am not going to lose any data in this current case. Now, if you are thinking that since I have a copy of the data into multiple broker nodes, when I'm trying to read data or when I'm accessing the data, which broker will be used to serve my data? The answer is, in Kafka, we have a concept of leader node. Now, inside that Kafka cluster, only one broker can serve data for a given partition. And that node is called a leader node. Let's assume for topic 1, my partition 0 leader node is broker 01, and for topic 2, partition 0, my leader node is broker 02. Other nodes in the broker, they will synchronize the data, and we call as in-sync replica. So in my current architecture, the partition 0 in broker node 1, that data will be replicated to broker node 2. Similarly, the partition 0 will be replicated here, and only one node will serve as the leader node, whereas the other nodes will be served as a in-sync replica nodes. And please remember this, for a Kafka cluster, for one topic, only one leader node, plus you can have multiple replicas based on the replication factor. I believe now you got a sense how Kafka replicates your data into multiple broker nodes and how you are getting the high availability, such that if one broker node will die, you will not lose any data. But if your replication factor is 1, in that case there is a chance that you are going to lose the data. Let's review Kafka Producer. Producer writes data into a particular topic. As we mentioned, that producer will first connect to any one of the broker node, and then the producer will specify the topic name. If I want to produce data into, let's say, topic 1 or into this blue topic, then I will connect to any one of the broker node. It could be broker 1, 2 or 3, and then I'll mention the name of the topic where I want to write the data. Here is a diagram to show how it will work. My producer, it will only specify the Kafka topic name, and then we have multiple partitions. Kafka will automatically distribute the data into different partitions, and these partitions will be residing into my broker nodes. Kafka automatically balances the load between these partitions. If we need an acknowledgement for my message, then we can configure message acknowledgement for data to write inside a topic. Here I have 3 modes. First is acknowledgement as 0, and that means no acknowledgement. I can have acknowledgement as 1. That means acknowledgement only from the leader node. And then there is a third configuration. I can use acknowledgement as all, where I am expecting acknowledgement from leader node and from all the replicas. Now let's understand this acknowledgement concept using diagrams. We have taken our previous example where we have one Kafka cluster and we have 3 broker nodes. Let's say we want to write data into this green topic, and my broker node 02, this is the leader node where I have partition 0, and then the broker node 01 and broker node 03 where I have in-sync replica. I am using replication factor as 3. That is why I have 2 copies. In the first mode of acknowledgement, my producer will write the data into the topic, and here the data will be written inside the topic and then data will be written into the leader node. But my producer will not expect any kind of acknowledgement, and this is the acknowledgement 0. As you see that since I am not waiting for any acknowledgement, I am only pushing the data. Now the data can be lost in the path, or data can be lost before reaching the broker. In that case, you will lose the data. Acknowledgement as 0, that is the fastest in terms of processing, but there is a possibility of data loss. Now AC case, this represent the acknowledgement or the message acknowledgement in Kafka cluster. Now there is a second mode, AC case equal to 1. In this mode, first a producer writes the data to the topic, then data will be written inside the topic, and then we will receive a confirmation from the leader. But if I have the replication factor set up, I am not waiting whether the data has been replicated to other brokers. That is why the acknowledgement equal to 1, there we have a chance of limited data loss, because after writing the data into the leader node, my data can be lost, or maybe at the time of replication, maybe other broker node can die. Then I can have limited data loss. But in terms of processing, since I am waiting for the acknowledgement, it will be slower in terms of the processing time. And the last acknowledgement mode is acknowledgement equal to all. First, my producer will write the data into the topic, then the message will be written inside the topic. Since I have replication factor set up here, now the leader node will send the data to all other in-sync replica nodes, and data will be replicated in my in-sync replica. Then the replica instance will send the acknowledgement of write, and once the leader node will catch all the acknowledgement from the in-sync replica, the leader node will send the confirmation back to the producer. In this mode, there is no chance of data loss, because I am waiting not only confirmation from the leader node, but from all other replica instances. And you can understand that in terms of processing, it will be the slowest among all. Now, if I want to explain using a graph, in this line chart at the left hand side, if I have no data loss, and if I have lowest write latency on the right hand side, then I can see the acknowledgement all, it will come in the leftmost. I will have no data lost, but in terms of latency, it will have a highest latency or the write latency. In terms of acknowledgement 0, it will be on the right hand side or extreme right hand, where I can have data loss, but it will be the fastest and I will have less latency. And acknowledgement 1 will stand at the middle. Now, based on your use case, if you have a very high sensitive use case, maybe your data, it can be recreated. You do not care about the data availability. In that case, you should select acknowledgement equal to 0. On the other hand, if your main application use case is the data persistence and you cannot afford any data loss, but your application is not that time sensitive in terms of processing, you can choose acknowledgement all. Now let's assume that I have multiple producers producing message into a Kafka topic. We reviewed Kafka automatically distribute the message between the partitions. and messages are ordered inside a partition. Then how am I going to get message order? My use case has a dependency on the message order. How can I implement the message ordering in Kafka? The answer is message key or Kafka message key. To maintain ordering, or if you want all your messages will be sent to a particular partition such that all the messages will have a proper ordering, you can send a Kafka message key along with your message. And the Kafka message key, it could be a string value or avro message. There are two different ways you can specify the key. You can specify the message key in record field, and you can use this particular syntax where you can mention the message key in a value, or you can use the message key as a record header also. So these are the two different ways you can pass the message keys. When you will pass a message key, the Kafka groups those messages into a single partition. Let's understand using this diagram. In my current example, I have 4 message keys and I am using game ID as my message key. Now I want the ordering of all these games data, and as I am using 4 different colors to represent those message keys, now I have 2 partitions here. I have 4 game keys and I have 2 partitions. So one partition may have 2 game data or 2 game keys. And in terms of partition 0, I'll have key for the orange or the yellow game and the blue games. And you can see as and when the games are coming, I have those ordering that will be maintained, and all those messages for that particular game ID will be clubbed into one partition compared to the previous, where Kafka can arbitrarily distribute those messages between the partitions. Whenever there is a message with the game ID 1, it will always go to partition 1. Whenever there is a message with game ID 2 or the green ID, it will always go to partition 1. Now when your consumer is trying to consume those messages, they will get those messages based on the order the message was created. And with this way, you will be able to maintain the ordering for your Kafka messages. Now, you must be asking how to handle duplicate messages. Let's assume my application cannot process duplicate requests and I want to implement only one-time delivery message. That means my messages should be delivered to my cluster or to my producers and it should come only once. How can I do that? The answer is Idempotent Producer. Using Idempotent Producer, we will be able to resolve this problem. Before explaining Idempotent Producer, let's understand the normal scenario. Let's say I have a producer and the producer is producing the message to Kafka cluster. Kafka cluster will commit that message and then it will send an acknowledgement. This is the good request. And now let's review a bad request where the producer writes the request or send that message to Kafka cluster. The Kafka cluster committed that message. However, before reaching that acknowledgement, there is a network error and the producer did not receive that message. My producer is thinking that commit has never happened. That is why the producer is again producing the message or send that message. Again, it will persist that message, which is going to create a duplicate commit in the Kafka cluster or a duplicate message, and I am going to get an acknowledgement. Now this is a duplicate request. To implement Idempotent Producers, we can enable Idempotent configuration. Now here is an example. If you are using Spring-based configurations, this is the way you can configure, or else you can enable idempotency in your producer. When you will enable idempotency, even if the producer did not receive that acknowledgement, and if the producer is sending one more request to persist the data into Kafka cluster, Kafka cluster will be able to understand that this is a duplicate message and it will not commit that message. Rather, it will send an acknowledgement to my producer. Now, so far we have reviewed Kafka producers. Let's review Kafka Consumer. And we already saw that Kafka Consumer, they are reading message from the topic, and consumer only specify the topic name and they need to connect to any one of the broker to read a message. Kafka will automatically pull data from the right broker because Kafka is intelligent and you really do not have to find out inside which broker your Kafka topic resides or inside which broker your Kafka partitions there. You need to only connect to a particular broker and you need to read the message using the topic name. Your producer is writing the data into the Kafka topic. Kafka will distribute the message into those top partitions. Now when the consumer will read, they will read the messages in order for a particular partition. We already mentioned messages inside a partition will have the ordering and we call it as offset. But messages between the partition will not maintain any order and the offset value is not valid between different partitions. Now consumer can process multiple partitions in parallel, and if I have only one consumer and 3 partitions, then my one consumer, it can process multiple partitions, or even I can have separate consumers per partitions. Other queues like SQS queues, when you process one message, the message will be automatically deleted or you are deleting after processing. Kafka is not like that. Inside Kafka, there is a data retention time. By default, it is 7 days and your message will persist for 7 days. You can have multiple consumers or multiple group of consumers reading the same messages. Maybe you have different purposes. Maybe you have one set of consumers which is processing those messages for AI ML or for the anomaly detection. You also have another set of consumers processing the data for the metrics generations or for the dashboards. Now in Kafka, we have a concept of consumer group. Let's assume that in my Kafka topic, I have 3 partitions, partition 0, 1, 2 and 3, and I have first set of consumers where I have 4 consumers which are reading the data from all those partitions. That I have a second set of consumers where that consumer is performing a different task, but both are parallelly processing the same message. The second set of consumers, I have consumer 2, which is parallelly processing partition 1 and partition 2. And we can create a group of consumers and we can create a logical group for those consumers. And let's assume I have consumer group A for the previous 4 consumers and I have consumer group B for these 2 consumers. As I mentioned, the consumers read data in consumer groups. Each consumer in a group reads from the exclusive partitions. 2 consumers cannot read data from a single partitions, but one consumer can read from 2 different partitions. Please remember this point. 2 consumers from a same consumer group cannot read data from the same partition. However, one consumer can read data from 2 different partitions. And you can't have more consumers than partitions that we have already discussed. If you have that, consumers will be idle. Now, if one of my consumer will die or bounce back, let's say my consumer was processing that message and then that consumer will die or it will bounce back. How my consumer will do the checkpointing, how my consumer will understand that at what point it has processed the request. To help with that, we have consumer offset. Consumer offsets are the pointers that every partition will have, and Kafka stores that offset at which consumer group it is reading. For my current example, for consumer group A, consumer 1 is reading from partition 0 and the current offset is 8. Consumer 2 is reading from partition 1 and the current offset is 7. Similarly, for consumer 3, it is reading from partition 2 and the offset is 10. My consumer 4, that is totally idle. Similarly, for consumer B, consumer 1 is processing from partition 0 and the current offset is 4. And consumer 2, that is reading simultaneously from partition 1 and 2 and the offsets are 8 and 7 respectively. Whenever the processing of the data will be completed, the offset will be committed to the Kafka topic. Let's say consumer 2 that process the data or the process the message 7 offset, it will persist this message 7 offset into Kafka topic. Now once a consumer bounced back, maybe consumer 1 while reading that message, it bounced back. It dies and again it came back. Since we have the offset, consumer 1 will be able to understand that for partition 0, I was reading from partition 0 and my current offset is 8. That means I have completed processing till 8 because offset will be persisted if at all the message will be processed successfully. While processing that message, if the consumer dies, then that offset will not be persisted. It will have the previous offset. When consumer 1 will be bounced back, it will be able to start processing after offset. That is, it will be able to start processing from message 9 or the offset 9. We came at the end of today's video. A logical next step would be to launch a Kafka cluster and create at least one producer to push the data to the cluster and one consumer to process the data from the cluster. If you want us to create a hands-on video demonstrating the step-by-step process or discuss top 20 Kafka interview questions, please leave your request as comment to this video. That was all for today. Thank you for your time and support. If you like our effort, please like, subscribe and share this video. We hope to get you in our next week video as well. Thank you.